Look around you, right now. Do it. What do you see? You see a room. You see walls. You see depth. You can stretch your hand out and feel the empty space between you and your screen. You feel the gravity pinning you to your chair. It feels real. It feels solid. It feels like a three-dimensional world. But here is the part nobody tells you. That depth, that gravity, that space you are moving through, it's a lie. It is a rigorous, mathematically proven hallucination. Physics is starting to realize something terrifying about our reality. We aren't living in a 3D universe. We are living on a flat 2D surface, and what you call reality is just a projection, a hologram, popping off that surface. Gravity isn't a force pulling you down. It's a side effect of information processing at the edge of the universe. That sounds like science fiction, I know. But if the calculations holding up modern physics are correct, your entire life is happening on a flat sheet of data. And I can prove it to you. Let me show you the trick. Look at your hand. Seriously, hold it up right now. Wiggle your fingers. You see skin, bone, muscle moving through empty space. You perceive height, width, and depth. This is the 3D world we evolved to survive in. It feels undeniable. But your eyes are lying to you. Think about a hologram on a credit card. It's a flat 2D sticker. You know it's flat. But when you tilt it under the light, snap, a 3D image pops out. You see a bird or a logo hovering in space. Your brain swears there is volume there, but there isn't. All the information for that 3D image is smeared onto a flat 2D surface. Now, here is the part that keeps physicists up at night. What if the entire universe is just that credit card? This is called the holographic principle, and it suggests that the 3D reality you are walking through right now is just a projection. The real you, the actual data describing every atom in your body, isn't actually here. It is plastered on a distant, flat 2D surface at the edge of the cosmos. We are the projection. We are the ghost in the machine. And gravity? That heavy feeling holding you to your chair? It's not a fundamental force. It's just a side effect. It is the pixelation of the projection. But to prove it, we have to start with a disaster. We have to try to destroy information. I want you to imagine a crime. Let's say you have a secret diary. You want to destroy it. So you throw it into a fireplace. You watch the pages curl and turn to black ash. You watch the smoke drift up the chimney. Gone, right? Wrong. According to the fundamental laws of quantum physics, specifically a rule called unitarity, that information is not destroyed. It is just scrambled. Here's the thing. If I were a super intelligent computer and I could capture every single particle of ash, every photon of heat from the fire, and every molecule of smoke, I could, in theory, reverse the movie. I could track the trajectory of every atom backwards and perfectly reconstruct your diary. The information, the specific arrangement of atoms that makes the diary yours, is immortal. In our universe, information is never lost. It just changes shape. This is the bedrock of physics. Without this rule, science falls apart. But the universe has a trash can. Enter the black hole. Imagine you throw that same diary not into a fire, but into a black hole. It crosses the event horizon, the point of no return. Swoosh! It's gone. It is crushed into the singularity. Now, for a long time, we thought this was fine. The book is just sitting inside the hole, right? But then, Stephen Hawking came along in the 1970s and dropped the bomb on physics. He discovered that black holes aren't perfectly black. They radiate energy. They glow. This is called Hawking radiation. Because they radiate energy, they lose mass. Over billions of years, a black hole will shrink and shrink and shrink until eventually, pop. It evaporates completely. It disappears from the universe. Here is the crisis. When that black hole disappears, where did your diary go? The radiation coming out of the hole is random heat. It doesn't carry the text of your diary. So when the hole dies, the diary is deleted, truly deleted, erased from reality. This sounds like a small problem. Who cares about a diary? You should, because this broke physics. If information can be destroyed, then the past implies nothing about the future. It means the foundation of quantum mechanics is a lie. It was a war between two theories. Gravity, black holes, said information dies. Quantum mechanics said information lives. They couldn't both be right. To save physics, we had to find a place where the information was hiding. And what we found? Well, it suggests that space itself is a misunderstanding, because the answer wasn't inside the hole. It was on the surface. I want you to think about entropy. It's just a fancy word for disorder. A messy room has high entropy. A tidy room has low entropy. Easy. But here's the trick. Entropy is also a measure of information. If I have a super messy room, I need a lot of information, a lot of data to describe exactly where every sock and every piece of dust is located. Now imagine throwing that messy room into a black hole. According to classical physics, black holes are supposed to be simple. They have mass, spin, and charge. That's it. They have almost zero entropy. They are smooth, perfect spheres. But wait, if you throw a messy room, high entropy, into a simple black hole, zero entropy, the total entropy of the universe goes down. Stop. That violates the second law of thermodynamics. Entropy must always increase. You can't just delete disorder. So Jacob Bekenstein, a brilliant physicist, asked a question that sounded insane. Does the black hole have entropy? Stephen Hawking said no. He said black holes are hairless, smooth, perfect. Bekenstein said yes. He said if you throw something in, the black hole must record it. But where? If the inside is a singularity, a point of infinite density, where do you store the data of a messy room? You can't write it on a point. Here is the twist. Bekenstein realized something profound. When you throw stuff into a black hole, the hole gets bigger. Its surface area grows. He found a specific relationship. The amount of information a black hole can hold is directly proportional to its surface area, not its volume. Read that again. In our normal world, storage is about volume. If I want to store more water, I need a bigger bucket, volume, 3D space. But for a black hole, the storage limit isn't the inside, it's the outside. It's the event horizon, the surface. Think of the event horizon like the shell of an egg. Bekenstein and Hawking eventually agreed. The information of everything that falls into a black hole isn't lost inside. It is smeared onto the surface of the horizon like a sticker. This is huge. It means a 3D object, your diary, a messy room, a star, can be completely described by 2D data on a flat shell. The inside of the black hole is just a projection of the data on the outside. Now pause. If a black hole, which is the most extreme object in the universe, stores its reality on a 2D surface, could the rest of the universe work the same way? Are we inside a black hole? This leads us to the smallest thing in existence, the pixel of reality. Let's zoom in. If I take a magnifying glass and look at your hand, I see skin. Zoom in more, I see cells. More, molecules. More, atoms. More, protons and neutrons. More, quarks. We keep dividing. We assume we can keep dividing forever. Space is continuous, right? Smooth like water? Wrong. There is a hard limit, a point where physics stops. It is called the Planck length. It is tiny. Specifically, 1.6 times 10 to minus 35 meters. To give you a sense of scale, if an atom were the size of the entire visible universe, the Planck length would be the size of a single tree on Earth. At this scale, space isn't smooth. It's grainy. It's pixelated. Think of your TV screen. From the couch, the image looks perfect. But if you press your face against the glass, You see the individual red, green, and blue dots. The universe is made of dots. Now, here is the problem. If the universe is 3D, filled with volume, we should be able to pack a lot of information into a box. We should be able to fill every single tiny 3D plank-sized cube inside that box with a bit of data, like filling a jar with marbles. The total information should be proportional to the volume, L times W times H. But when physicists tried to calculate the maximum amount of information you can pack into a region of space before it collapses into a black hole, the Bekenstein bound, they found something disturbing. The maximum amount of information you can store in a region of space isn't proportional to its volume. It's proportional to its surface area. This is the key. Imagine you have a room full of books. The amount of information in that room should depend on how many books you can stack inside. But the math says no. The maximum information depends only on how many book covers you can tile on the walls, floor, and ceiling. The inside doesn't matter. The volume is irrelevant. This means the inside of space, the 3D part where you and I live, isn't the fundamental reality. It can't hold more information than the surface can describe. If the surface contains all the data, then the volume is just a projection, a hologram. So, if we are inside a giant cosmic room, where are the walls? Where is the surface that contains us? To understand that, we need a can of soup. Okay, here is the analogy that will change how you see the world. Imagine a can of soup. This can has two parts. First, the bulk. This is the inside, the delicious tomato soup. It has volume, it has depth, it's 3D. You can stir a spoon through it. Second, the boundary. This is the label, the metal cylinder, the surface. It has height and circumference, but no depth. It's 2D. You can unroll it flat like a poster. Now, imagine this can represents the entire universe. The bulk is where we live. This is space, galaxies, stars, you, me. We are swimming in the tomato soup. We feel gravity. We move up, down, left, right, forward, back, 3 dimensions. The boundary is the edge of the universe. It's infinitely far away. It's flat. It's 2D. No gravity, just quantum fields living on a surface. Here is the bombshell. In 1997, a young physicist named Juan Maldacena discovered something that shocked the world. It's called the ADS-CFT correspondence. ADS stands for anti-de Sitter space, which is a fancy way of saying a specific type of curved, soup-filled universe, the bulk. CFT stands for conformal field theory, which is quantum mechanics without gravity, living on a flat surface, the boundary. Maldacena proved that these two worlds are mathematically identical. Wait, think about that. He showed that everything happening in the 3D soup, every star collapsing, every planet orbiting, every thought in your brain, can be perfectly described by equations on the 2D label. There is a 1-to-1 mapping. If a spoon moves in the soup, a ripple moves across the label. If a star explodes in the bulk, a specific pattern of quantum fields flashes on the boundary. They are the same thing. It's like a video game. When you play Call of Duty or Minecraft, you see a 3D world. You see depth. You see mountains in the distance. You see enemies hiding behind walls. But where is that world actually located? It's on a 2D microchip. It's just a stream of ones and zeros processing on a flat silicon wafer. The 3D world is a projection, a simulation. Maldacena's discovery suggests that our universe is exactly like that video game. The 3D world we experience, gravity, space, time, is just the user interface. The real physics, the source code, is happening on the 2D boundary at the edge of the cosmos. We are characters in a holographic movie, convinced that the screen has depth. But if gravity is just a projection, what is it? Why do we feel it? This is where it gets truly mind-bending, because gravity might just be pixelation. Wait, stop. If we live on a flat 2D boundary, how can I pick up this pencil? How can I feel weight? Gravity is real, right? It pulls me down. Here is the twist. On the 2D surface, the label of the soup can, gravity doesn't exist. Read that again. On the boundary, there is no gravity. Just quantum fields buzzing around. No heavy objects, no falling, just data. But when you project that data into the 3D bulk, into the soup, something magical happens. Gravity emerges. It appears out of nowhere. It is an emergent property. Think about temperature. What is heat? It's not a thing. You can't hold a heat particle. Heat is just the average motion of atoms jiggling around. If you zoom in to a single atom, it doesn't have a temperature. Temperature only exists when you have many atoms. It emerges from the group behavior. Gravity is like heat. It is the temperature of space-time. It is the statistical result of quantum entanglement on the boundary. When two particles on the 2D surface get entangled, spooky action at a distance, they create a connection, a thread. Multiply that by trillions of particles. The threads weave together. They form a fabric. That fabric is space. And the curvature of that fabric, that is gravity. So when you feel the earth pulling you down, you aren't feeling a fundamental force of nature. You are feeling the geometry created by quantum information processing on the edge of the universe. The more entangled the boundary is, the stronger the gravity in the bulk. Gravity is literally the resolution of the hologram. If the boundary had infinite resolution, gravity would be perfect. But because the boundary is made of discrete bits, pixels, gravity is grainy. This explains why we can't combine quantum mechanics, small stuff, with general relativity, big stuff. They speak different languages. One speaks in pixels, the other speaks in smooth curves. But the holographic principle translates between them. It is the Rosetta Stone. It says that a black hole in 3D is just a hot soup of particles in 2D. A galaxy in 3D is just a swirl of data on the boundary. And you? You are a 3D avatar of 2D code. Now this sounds like philosophy, but it isn't. It's math. And the math is so powerful, it solved a 50-year-old paradox in a single afternoon. Let's look at the proof. Let's be real for a second. String theory, you've heard of it. It's infamous. It's complicated. It requires 10 dimensions. People roll their eyes at it because it's so hard to test. But in 1997, Juan Maldacena used string theory to perform a miracle. He didn't just propose the holographic principle as a cool idea. He proved it mathematically for a specific type of universe. Here is what he did. He took two completely different theories that had nothing to do with each other. Theory A, quantum field theory, QFT. This describes particles on a flat 2D surface, no gravity, just the standard model, like the soup can label. Theory B, string theory in anti-de Sitter space, ADS. This describes gravity in a curved 5D universe, like the soup inside the can. These two theories look like they're from different planets. They use different math, different variables, different rules. One has gravity, the other doesn't. One is 5D, the other is 4D, or 2D, 3D in simpler models. But Maldacena found a dictionary. He showed that every single calculation in Theory A has an exact partner in Theory B. If you calculate the energy of a particle on the boundary, you get X. If you calculate the mass of a black hole in the bulk, you get X. They are identical. It was like discovering that English and Chinese are actually the same language, just written in different alphabets. This is the strongest evidence we have for the holographic principle. It's called the ADS-CFT duality. It means that gravity and quantum mechanics are just two different ways of looking at the same reality. One is the hologram, the other is the image. Now, critics will say, but our universe isn't anti-de Sitter space. Our universe is expanding and flat, not curved like a saddle. True. We don't live in a soup can. We live in an expanding bubble. But the principle holds. The math works too perfectly to be a coincidence. If it works for that universe, it likely works for ours too. It suggests that the deep structure of reality is holographic. But math is just numbers on a page. Physics requires experiment. We need to see the pixels. Can we actually detect the graininess of space? Can we hear the hologram? Believe it or not, we are trying right now. Hold on. You can't just assert that the universe is a hologram without checking it. That's philosophy, not science. We need a test, a real one. Enter the Fermilab holometer. This is a real experiment built in Illinois. It sounds like something out of Star Trek. It uses twin laser beams to measure the fabric of space-time itself. Here is the idea. If space is truly continuous, if it's smooth all the way down, then the lasers should travel perfectly straight, no jitters, no wobble. But if space is pixelated, if it's made of discrete Planck-sized bits like a Minecraft world, then the lasers should encounter holographic noise. Imagine driving a car on a perfectly smooth road versus a road made of tiny cobblestones. On the smooth road, the ride is silent. On the cobblestones, you feel a vibration. The holometer is listening for that vibration. It is trying to detect the jitter of space itself. If they find this noise, this specific, irreducible fuzziness, it would mean that space has a minimum resolution. It would mean that reality is pixelated. And if reality is pixelated, it strongly supports the holographic principle. It would mean that the total amount of information in the universe is limited. It would mean that the pixels on the 2D boundary are projecting a blurry 3D image, and we are just now noticing the blur. Now, full disclosure. The first run of the holometer didn't find the noise they were looking for. It was inconclusive. The universe is incredibly smooth. But that doesn't kill the theory. It just means the pixels are smaller than we thought, or the noise is harder to hear. But other experiments are ramping up. We are looking for quantum gravity signatures in the echoes of the Big Bang. We are looking for patterns in the cosmic microwave background radiation. Physicists are desperate to find this. Why? Because if we find it, it changes everything. It confirms that space is just a construct. It confirms that the 3D world is an illusion. And if the 3D world is an illusion, what does that make us? Are we real or are we software? This leads to the most disturbing question of all. Here is the twist, the one you've been waiting for. If the universe is a hologram, if the 3D reality you see is just a projection from a 2D surface, and if that 2D surface is just bits of information processing, then what is the difference between our universe and a computer simulation? Think about it. In a computer, everything is just ones and zeros on a hard drive, 2D. But on the screen, you see a rich 3D world, hologram. The holographic principle doesn't say we are in a simulation. It says the universe is information processing. It says that physics is computation. It from bit, that was John Wheeler's famous phrase. Every it, every particle, every field, every force comes from a bit of information. Reality is code. And if reality is code, then the laws of physics are just the operating system. The speed of light is the clock speed of the processor. Quantum mechanics is the error-correcting code. This aligns perfectly with simulation theory, the idea that we are living in a matrix. But there is a catch. In a simulation, there is a programmer, someone outside the box running the code. In the holographic principle, there is no programmer. The code runs itself. The boundary is the computer. The universe computes its own future. We aren't characters in a game played by aliens. We are the game itself. We are the math waking up and realizing it exists. The boundary conditions at the beginning of time set the rules, and the rest is just the inevitable unfolding of the algorithm. So, are you real? Yes. You are real information. You are a complex pattern of data processing on the edge of the cosmos. Your feelings, your memories, your consciousness, they are all valid. They just aren't located where you think they are. You aren't inside your head. You are smeared across the horizon of the universe. And that leads to the final thought. So where does that leave us? I started this video by asking you to look at your hand, to feel the depth, to trust your eyes. But physics has pulled back the curtain. We have learned that gravity is an illusion. We have learned that black holes are just hard drives. We have learned that the universe is pixelated. And we have learned that we might be living on the surface of a bubble, projecting a 3D movie called reality. This is the holographic principle. It's not just a theory, it's a map. A map that shows us where the treasure is buried. It tells us that the universe is far stranger than we ever imagined. It tells us that space and time are not fundamental. They are emergent. They come from something deeper, something simpler, information. The universe is made of bits, and those bits are you. You are not insignificant. You are not just dust in the wind. You are a unique, irreplaceable pattern of information woven into the very fabric of the cosmos. And even if you fall into a black hole, the universe will never forget you. Your data is eternal. It is written on the horizon of forever. The next time you look up at the stars, remember this. You aren't looking out into space. You are looking at the projection screen. And the real you is somewhere else entirely, watching the movie.